We will continue with the post-processing, and we will cover two topics. One is the velocity vector, second is the XY plot for the YPlus. So first the velocity vectors. You can use the velocity vectors from the post-processing tab on the top of the screen. Click and then click on the edit. Or you can go to the tree outline, and from tree outline click on graphics, and from graphics click on the vectors, double click, uncheck all the surfaces or the boundaries, and then click on the save and display. Change the scale to the 10. Zoom the geometry in the leading edge of the aerofoil. And you can observe the development of the boundary layer on the aerofoil. So by changing the scale of the vectors, for example 5, you can clearly see that we have the boundary layer development on the upper surface of the aerofoil. So similar to the velocity profile we see in the flat plate. So boundary is growing, and you can see that the profile is increasing in the depth or in the thickness. And at some point at the trailing edge, the velocity is almost 0. Okay, next thing is to display the YPlus plot at the, because this case we solved at the 10 degrees angle of attack, and when you solve this case at the 0 angle of attack, you will notice that the YPlus plot on the both surfaces will be having the same value, because the both surfaces are feeling the same flow, same acceleration, so same condition. That's why the YPlus value or any other variable will be of almost of the same value. So go to the XY plot and then choose the y axis function as a turbulence, and in the turbulence select the wall y star y plus, and the x-axis we will be displaying the direction vector which is along the chord length of the aerofoil, and in the surfaces select the aerofoil. On the leading edge, you will notice that the YPlus value is the highest value, because here the velocity is almost negligible. And all the velocity has been changed into the fractional part, so you will notice that the value is very high on the leading edge, and especially when the flow is going on the upper surface, it's accelerating. And then on the pressure and the suction side, on the upper and lower surface, the value will be lowered down, and maximum value we are getting is 20, and on the average you will notice that the value is around 4 to 6. And for the hybrid valve functions or the universal valve function which are implemented in the fluent, the value should be less than the 10. So here we are getting the value approximately 6 or 4. So this is good value for the YPlus to get the drag and the lift coefficient. And also you can see that we are not plotting the YPlus. You can also plot the YPlus, which is by definition is the friction velocity first cell height density divided by the viscosity. Here we are plotting the Y star, because Y star is the parameter which is similar to the YPlus, but it depends on the turbulence model. So maybe YPlus is same for all turbulence models, but the Y star will be different for the different turbulence model. This depends on the turbulent quantities, not the simple flow properties, but they depend on the turbulent quantities. So let me show you. Double click on the plots to open the plots option, and then double click on the XY plot. From the y-axis function, choose the turbulence, and in the turbulence choose the wall Y star, and keep the default option for the x-axis function, which is the direction vector, and choose the aerofoil, and then click on the plot. So same variables are here, same values. You can change the axis, or you can change the curves option. So you can put some symbol here, apply, and then again plot. You can change the color also. You can change the color of symbols also. Let's say we make this one as a dark red. You can also change the scale on the x and y axis. So on the axis you can change the number format. Let's say you change it to the general. So the values are from the 0.1 and up to the 1. And also on the y-axis you can change the number format to, let's say, to the journal. We can also check that what will be the effect of changing the variable to the YPlus. And as you can see here that in the both cases the YPlus value is not different or not changing. This shows that in this case the value we are getting from the YPlus and from Y star, they are same values. But in some cases, for example, in the case when we are using the scalable wall functions, these both values will be the different values, because the scalable wall function will limit the value of YPlus, which is a Y star, to the 11. So maybe we have the YPlus equal to the 0.1 or 0 or the 5. But the Y star will be limited to the 11.06. So any value which is less than this value will not be shown on your computer screen. The next thing is to plot the XY plot for the CP, which is the coefficient of pressure. And the CP is defined as the pressure minus the P infinity, which is the pressure at the free stream, which is 101325, or in our case it's a 0. And divided by the aerodynamic pressure, which is 1/2 density of the free stream flow into the velocity square, which is again free stream velocity, which is coming from the outside to the domain. So in the XY plane, choose the pressure coefficient, choose the aerofoil, and then plot. And it depends on the value of the reference conditions, which we have already set for this case. So if you notice that the reference conditions are set, and they were taken from the inlet, and the area was given as a 1 meter square, and depth is a 1, length is a 1. Density is 1.225, velocity is 43.822, viscosity is same as we have given in the material panel. So we have the maximum pressure coefficient is a 1, and the minimum is a -5. This is happening on the upper surface where we are having the velocity or the acceleration of the flow, and on the bottom surface it is almost constant value and it is approaching 0 value. And then at the trailing edge they are joining each other and they are going to be the 1 value, and then after it will exit from the aerofoil trailing edge.